right, so this morning we learned a lot about, hopefully we learned a lot about the functional groups in organic chemistry. And I sort of wanted to focus on the functional groups in amino acids for a reason. And one of the reasons was we're going to be doing this lab today on enzymes. And the important thing to remember about enzymes is that all the chemistry, all the reactions that take place within enzymes generally deal with those functional groups that we talked about this morning. There's acids, there's bases, there are sulfur groups, there's amines, there's all these things that are placed in a very specific three-dimensional space in an enzyme for these reactions to take place. And so I sort of wanted to address a little bit of that before we did the experiment. And the experiment hopefully will teach us a little bit more about enzymes. Going further, we'll learn a lot more about polypeptides and proteins and how they're put together. But we're going to learn a little bit about the reactions they catalyze and the effects of concentration of the enzyme, the pH involved. The pH is extremely important when we're dealing with enzymes and their activity, as well as the temperature. So let's have a look. So the enzyme we're going to be using today is one we used in a previous experiment. Remember, we used yeast in another experiment with hydrogen peroxide, and the yeast has an enzyme in its surface called catalase. I sort of mentioned at the time that it was one of the first enzymes that was discovered, and that's why I sort of got the name catalase, because it catalyzes a reaction. Now, when it says enhances the decomposition of hydrogen peroxide, what does that mean? It enhances it. Anyone give me sort of like a brief rundown of what enhances means? Accelerates, yeah, big time. That's basically what enzymes do. Enzymes, if it's a reversible reaction, and we'll talk a little bit more about this a little bit later, if it's a reversible reaction, they can't really affect how far forward or how far back the reaction goes. But what it can do is speed up that reaction tremendously. And we'll go over one of the reasons why that is. So what we're going to do is look at this enzyme and see, we're going to be measuring how fast it catalyzes this reaction of hydrogen peroxide breaking down into water and oxygen gas. And notice that this isn't balanced. I apologize. But we're going to be looking at the production of oxygen, because since it's a gas, it will rise. And what we're basically going to be looking at is, it forms bubbles in liquid, and we're basically going to be plotting how fast those bubbles are going to take a piece of paper and have it go from the bottom to the top. So we're going to measure the effective concentration. If we have more enzyme, will that speed up the reaction? Will it slow down the reaction? We'll look at the effects of temperature. Generally, with a reaction, do reaction rates generally go down with temperature when temperature goes down, or do they go up when temperature is increased? So if temperature goes up, what generally happens to the rate of a reaction? Does it generally go faster or slower?
Faster.
Generally, it goes faster, right? And that's the case even without an enzyme. And the reason for that is if you have two molecules, basically, if you had hydrogen and oxygen and they come together and form water, the faster those molecules hit each other, the greater the energy they hit one another, the faster the rate will be that they'll interact with each other and then form a compound. We'll also see that things tend to break down, tend to decompose faster with increased temperature. That's not always the case. There are certain reactions like exothermic reactions. Some of them tend to go down at higher temperature, but most reactions increase the speed with the effect of with increased temperature. And then we're also going to look at the effects of pH on activity. And pH can have a really profound effect on activity of an enzyme. For instance, if you had a carboxylic acid in an enzyme and you needed to have this oxygen have a negative charge for this reaction to occur, the higher the pH, the more likely that this is going to be protonated. And so that negative charge will be gone. And so we might expect that as the pH goes down, the rate of the reaction goes down also. On the other hand, if you had an amine group and you needed to have that amine group have a positive charge for the reaction to be catalyzed, as you lower the pH, you get more and more and more protonation. And that, if this is required for that reaction to take place, the rate of reaction would actually increase if the pH goes down. And we'll also learn that with a protein, as you change the pH, sometimes you'll change the pH so drastically that the protein will then fall apart, that the protein will actually unfold and what we say precipitate. It will crumble. And so we need to see at the extremes of pH, like pH 1, pH 11, pH 12, at these extreme pHs, that the protein may not be stable. And so if the protein isn't stable, it can't catalyze the reaction. So we're going to see what the effects of pH on this reaction are. And it's really kind of difficult to predict what the effects of pH are going to be. We can generally predict what the effects of concentration will be. More enzyme typically goes faster. As the temperature increases, typically the reaction goes faster. But the effect of pH can be really unpredictable. And so we'll learn what that does today. So here's something that you may or may not be familiar with in terms of reactions. Has anyone heard the concept of activation energy before? Is this a new concept for folks? Ryan's shaking your head. So it's a new concept or it's an old one?
It's an old concept for me.
Okay, cool. So you can teach the rest of it then. So what activation energy is that basically at the beginning, this is called a reaction path. Whoops, let me go back. This is called a reaction pathway. And what a reaction pathway is at the beginning over here, you just have reactants. So at this point, you would just have hydrogen peroxide. And as we go across the reaction pathway, at the end, we would have our products. So we would have water and we would have oxygen. And then midway in between, we have something called the activated complex. What does that mean? Well, with any reaction, you got to break some bonds and you have to form some bonds. So for the activated complex to form, you basically need to stretch this oxygen oxygen bond. You need to stretch it so it becomes easier to break. And in doing that, that takes some energy to do. So you need to like physically move those oxygen atoms apart. That takes energy to do that. And at the same time, as you're moving those apart, you need to allow other parts of other molecules involved in the reaction, like water, parts of the enzyme, to get involved. You need them to move into place. So you have higher energy. You have high energy at the beginning, meaning you have bonds that need to be broken. And as you make products, you form bonds and the energy is decreased. As you're breaking bonds, that takes energy to do. As you're forming bonds, that releases energy. Much like when we're burning wood, for instance, we have a lot of energy in those carbon-carbon and carbon-hydrogen bonds. These aren't particularly strong bonds. They're non-polar. They're not particularly strong. What they get converted into is water, which has much stronger bonds. Those oxygen-hydrogen bonds are stronger, and carbon dioxide, which has very strong carbon-oxygen double bonds. And so you go from a high energy, weak bonds to lower energy, strong bonds. And in the middle up here, you need to add energy to sort of you need to start breaking some of these bonds in the reactants, and you start forming some of those bonds in the products. And so it takes a certain amount of energy to get to this place. So if you don't have an enzyme, it takes more energy. Why is that? Well, with the enzyme is given this line here. So this line here is the same reaction, but occurring with an enzyme. What the enzyme does is actually stabilize this complex. So this complex is unstable. You're stretching bonds, you're forming new ones. It's an unstable complex. But inside the enzyme, you have all of those amino acids with the groups we talked about this morning are interacting with that complex. They're forming intermolecular forces. They're forming intermolecular bonds with that unstable activated complex. And the more interactions you can form, the more stable it is. And so you need much less energy in forming it with an enzyme than you do without the enzyme. And so you get the same products, you get out of the same reactants, but the rate of the reaction, how fast this reaction goes, is all due to this energy difference right here. So if you need to put a lot more energy into the reaction to get it to go, it goes a lot slower. If it takes a lot less energy for that reaction to go, it goes a lot faster. And so that's basically how enzymes make the reaction go much faster. They lower what's called this activation energy barrier. A lot of times it's called just an activation barrier. And it's called a barrier because it's basically preventing that reaction from taking place. So wood just sitting around does not, even though the products of combustion are much more stable than the wood by itself, it doesn't spontaneously happen. You need to add some energy to get that reaction started. You need to strike a match. You need to do some sort of chemical energy, or you need to do, like if you're a Boy Scout, you need to do like put physical energy in there to get enough heat to get that reaction to start. Once it's started, then it's self-sustaining. The energy from the combustion generates activated complex for more combustion to take place. but energy needs to go in the first place in order to get that reaction to go. That's true for pretty much all reactions. There's very few just spontaneous reactions that happen all by themselves. Generally, you need to add some little bit of energy to go. And down here in the corner, you can see basically how that works. So you've got, so you've got something called a substrate. A substrate of an enzyme is basically, those are the reactants, are called the substrate. And they will fit in the enzyme. They'll be stabilized by the shape of the enzyme. And then also it will stabilize the activated complex. So the substrate goes from being a stable complex to being a slightly more unstable complex as it gets turned into the activated state. And then finally, once the reaction occurs, the products get released, because the enzyme has a much higher, what we call affinity. The substrate or the reactants fit perfectly into the enzyme. The products don't. And it's important that the products don't, because if the products fit in there too, they'd never be released. So we want the enzyme to bind the reactants, hold on to them fairly tightly, and then once the reaction takes place, release the products. So then the enzyme can go through another round. So one enzyme can catalyze millions of reactions in a second. The faster they get rid of the products, the faster they can bind more reactants. So here is the actual mechanism that's been thought of for catalase. So here we have our reactant, and what it does is it binds to an iron. You see this a lot with enzymes. A lot of them will have metallic centers in them. A lot of them have, like hemoglobin, for instance, has iron in it. A lot of them have copper. Some have zinc. But a lot of them will have a metal in the middle. And the reason for that is they interact with oxygen. And here, the interaction with oxygen is, the first reaction is one of the oxygen atoms gets pulled off of the hydrogen peroxide, and it forms a double bond with the iron. That releases water. So our first part of the reaction has taken place. We've got one peroxide molecule went in and a water was released. But we're not done, because we still have this oxygen bound to the iron. So what happens is a second peroxide molecule goes in, and it interacts with the oxygen that's bound to the iron. So one of the oxygens from the peroxide interacts with this oxygen. They form a compound, oxygen, and that's released. And then the water is also released. And notice what happens to the iron. And this is critical for an enzyme. Notice that after the first step, the iron forms a covalent complex with the oxygen. And then it releases that oxygen and goes back to what it looked like originally. So it was an iron 3 complex bound to the catalase enzyme at the end, and it goes back to being an iron 3 enzyme complex at the beginning. And that's critical, because if what an enzyme does, what any catalyst does, it's supposed to, at the end of the reaction, remain unchanged. So it doesn't mean that it doesn't get involved with the reaction. It doesn't mean that at all, because it actually forms covalent bond with the oxygen. But notice it forms a covalent bond and then it breaks that covalent bond. So it goes back to what it looks like at the beginning. And so for an enzyme to work, it has to go back to exactly what it looked like in the first place. So it forms a complex and then it releases it, forms it, releases it. So it needs to look at the end like it looked at the beginning. So this is the product we're going to be looking for. We're going to be looking for the production of oxygen gas. So notice that what the enzyme actually does is take something that is toxic. Peroxide is extremely reactive, and so you don't want that. This oxygen-oxygen bond is quite unstable, and it breaks fairly easily. And what you're left with is, of these two electrons in this bond, this oxygen gets one of them, and this oxygen gets the other one. So what you have is an oxygen with an odd number of electrons. And I think we remember that an even number of electrons, cool, odd number of electrons, not cool. And so we have an unpaired electron. And so this unpaired electron in an oxygen just runs around just stealing electrons from everybody. And so it's really, really, really reactive. And so what the catalase does is it turns a very toxic reactive molecule into water and oxygen, things that are much, much more stable and non-toxic. Clear this. Okay. So we're going to be looking at, we're doing 3 different activities. I'm going to do one of them with you, and you don't really have to do all of them today. The effective enzyme concentration is fairly straightforward. The effect on temperature is fairly straightforward. The effect on pH is, it takes a lot of setup. So read the instructions really carefully, because if you'll notice, I know everyone's read the instructions before starting the lab, right? If you'll notice, there are a lot more steps than we're used to, like, 20, 30, 35 steps. So you got to be read them really, really carefully. So the first one, we're just going to make a catalase solution. We're going to take 2 grams of yeast and mix it with 250 mils of water. And then just let that dissolve, let the catalase be released from the dried yeast into the water. And then we're going to use 0% catalase, 25% solution, 50% solution, 75% solution, and 100% solution. So what we'll do is we'll take little discs of filter paper. Hopefully, if you don't have one hole punch to make these little discs, you can cut them out. Just make sure they all get to be the same size. And what we're going to do is soak the filter paper in these different solutions. So we're actually basically going to impregnate the filter paper with enzyme. Put them into a cup that has hydrogen peroxide in it, push it down to the bottom with a set of forceps, and basically wait for the oxygen bubbles to push the filter paper back up to the top. And presumably, the more concentrated our solution is with enzyme, the faster that should go. So the first activity will be looking at how much changing the amount of enzyme affects the rate, because that's basically what we're going to be measuring, is the rate of movement of the filter paper. How fast does it move? So we're going to measure the distance in millimeters, and we're going to measure how much time it takes in seconds. So our rate of movement will be millimeters per second. So any kind of rate has to have some sort of like a distance or a volume or something versus time. And that's going to be our reaction rate, the movement of the disk in millimeters per second. So the second one will be changing the temperature. We're going to look at room temperature, wherever you are, 10 degrees above it, 10 degrees below it, 20 degrees above it, 20 degrees below it. And then with pH, we're actually going to look at a really wide range of pH using, we have HCl, we have a hydrochloric acid solution in the kit, and we have a sodium hydroxide solution. So we're going to look at the effects of pH, I think all the way from 1 to like 12. So it's a pretty wide range. All right, let's look and see how we're going to set this thing up. So you need a lot of stuff for this one. So the kit comes, this one particular bag I've noticed has the yeast in it, has a piece of filter paper in it, the 2 medicine cups, there's a 24 well plate, which is really useful for doing dilutions. If you want to do like a series of dilutions, having a plate like that is really makes it a lot easier. We have 4 pipettes that we're going to be using to measure both the enzyme solution and water. So we'll have different concentrations. The 0.1 molar HCl, 0.1 molar NaOH. The beaker is what we're going to be mixing our yeast up in. One of the small glass test tubes you're going to be using later. The ruler, because you want to be measuring how deep the solution is that you push the disc to the bottom, because that's the distance we're going to be measuring. The bottom of the what is it? We're going to be putting the discs in one of these medicine cups. How deep it is for it to move from the bottom to the top of the solution. You want to look for the blue forceps in there. Going to be using those quite a lot in this one. Both graduated cylinders, spoon to do your mixing, something to mark. If you don't have a wax pencil, you can use a Sharpie. That works too. Weigh boat for weighing the yeast, balance obviously for getting the mass of the yeast, and the thermometer is going to be super critical. The kit comes with a 3% hydrogen peroxide. Basically, all hydrogen peroxide for home use is 3%. So if you already have some, like I already had some, so I'm just going to use that. Make sure it's 3%. I think sometimes you can find 5%. But we want to use 3%. We're going to be diluting it to half that, so 1.5%. So yeah, preparation, you're going to really want to read through the whole lab. And again, like I said, you don't have to do all of it today. I would probably recommend that you do the 2 easier ones today, then maybe the third one either later or tomorrow or some other time. So you want to punch out, if you have a single hole punch, which I really recommend you have. I luckily found one in my son's room. So you want to punch out 30 discs from the filter paper that you're given. Oh, damn it. Come on. If you don't have it, then you want to cut the filter paper into squares. Just take the ruler and make a grid. Squares should be like 6 to 7 millimeters a side, and then just cut them out. Make sure that they're really all the same size, because obviously if you have different masses of filter paper, it's going to take different lengths of time for get them to be pushed up. So we want to get around 35-degree temperature, because most enzymes, not surprisingly, work at around body temperature. All of the enzymes in your body pretty much have been optimized to work best at 37 degrees, because that's the temperature they're at. Same with these yeast enzymes. So for it to get to work the best, you want a temperature of around room temperature, body temperature. So you want to have a hot water tap, get it to about 35. So you have about 250 mils of that in the beaker, and then put 2 grams of yeast in there. That's going to be your 100% catalase solution. And it recommends for this particular lab, if it takes more than an hour to do one particular lab, just make another batch of catalase. Just get another 250 mils of 35-degree water and another 2 grams of yeast, and just make another one. Because like most enzymes, most proteins, if you leave them at a high temperature for too long, basically then they start to unravel and they lose their ability to catalyze reactions. So proteins don't stay the same forever. So you need to make a fresh solution if you want maximum yield, if you want them to work at the maximum amount. So one of the medicine cups will be 100% catalase, and you're just going to be using that as your 100%. Pour it up to like the 20% mark. Then each of these bulbs, it's like 4 bulbs in here. One you're going to be label just peroxide. Second one's going to be enzyme solution. Third one's going to be acid. Fourth one's going to be base. Okay. So let's look and see how we do the first one. So that's just getting your stuff ready. So you make a 20 mil solution of 1.5%. So 10 mils of 3% peroxide, 10 mils of water. Put that in one of the medicine cups. That medicine cup is actually what you're going to be doing the reactions in. So in the plate over here, so here's your 24 well plate. You're going to be making, and you can label this one too, or you can just put it down on a piece of paper and label the paper. So in the first well, you're going to have just water. So 20 drops of water using your pipette and no catalase. And then basically each well will have 20 drops in it with a different ratio of water to your catalase solution. So you go from 25%, 50%, 75, 100, following this particular formula, okay? So to do the reaction, you take your discs and you soak them in these wells. You only need to make one well each. So you take the disc, you soak it in either the 0, the 25, the 50, the 75, whatever it is, soak it in there, take it out, blot it, and then transfer it to the 20 mil solution of the 1.5% peroxide. You're going to measure the distance from the bottom to the top of the solution. That's going to be your distance. You push that disc down to the bottom with the forceps and you start a timer. So you just use your cell phone, start a timer and see how long it takes for it to reach the top. And we're going to do that 3 times for each concentration of catalase. Okay, so time in seconds, how long it takes the disc to go from the bottom of the 20 mil medicine cup to the top till it floats on the top. You take the used disc, toss it, and then do 2 more trials with a new soaked disc. So we'll do 3 trials for each one, and we record the time in seconds in our data table number one. Now remember, when you do your report, I want titles for these. I've actually put in, and people didn't notice this last time, I put title, like Scooby-Doo. And so a lot of people just left that there. I want this to be replaced with an actual title for each data table. So calculate the rate of each of those reactions, where D is the distance, T is the time, and so the rate will be distance divided by time. And then we're going to make some plots. So remember, we did the plotting lab the very beginning. So what we're looking for is a plot of concentration on the y-axis. I'm sorry, concentration on the x-axis, and the rate on the y-axis. And so we should see the higher the concentration of enzyme, the faster the rate. We should see that. We don't know whether it's going to be linear or whether it's going to be what kind of shape that's going to be. That's what you're going to be plotting. Right, let's look at, so that's basically the first one. That's looking at the effect of concentration. The next one is the effect of temperature. So with temperature, you're basically just going to make a water bath. And a water bath would have either ice in it or hot water in it. So what you do is basically you put the 20 mil medicine cup that has the peroxide in it into the ice, put the thermometer in there, and once it gets 10 degrees below room temperature, then you do your reaction. And so we do that one 3 times. So we look at room temperature, 10 degrees above, 20 degrees above, 10 degrees below, 20 degrees below. So we just either heat it in hot water till it gets to 10 degrees, take it out, do our reaction, or leave it in there for 20 degrees. Actually, oh, what do we have? 10 degrees below, 10 degrees above, 20 degrees above, oh, and 30 degrees above. Ooh, hot, hot, hot. So whatever, so measure, it's important to measure your room temperature. And then we're going to be doing each of those 3 times as well. And we're using 100% catalase for each one of those. So we won't be diluting the catalase this time. So each one we're using 100%. And then for the last one, we're looking at the effects of pH. And so it's really important to read the instructions really carefully, because there's a lot of serial dilutions in this one, where you're going to be taking, 5 drops from one well and putting it in the next one, and then taking 10 drops from that and putting it in the next one. So read that one really, really carefully. But basically what we have is adding HCl to 5 wells and adding sodium hydroxide to 5 wells. And then read the instructions really, really carefully, because we're going to go from pH of 1.3 all the way to 12.7. So basically that's a huge range in pH. And again, doing this reaction 3 times each and doing the average. Looking at how does pH impact the rate of the enzyme. This one is a lot, like I said at the beginning, this one's a lot more difficult to predict, because we don't really know what the optimal pH is going to be. It's probably going to be somewhere around 7, but we don't really know that for certain. It might speed up a little bit at slightly acidic or slightly basic pHs. So these are the 3 data tables. So that we're to be looking at the different times it takes. So from each trial, let's say it takes, 45 seconds, 48 seconds, 42 seconds. Then we take the average, let's say 45 seconds. If the depth of the solution is like 20 millimeters, then we would the rate of the reaction would be 20 millimeters over 45 seconds. And you want to get that per second. So the rate you're going to be plotting is millimeters per second, okay? So that's table 1. Table 2, again, with 5 different reaction conditions. 10 degrees below room temperature, room temp, 10 above, 20 above, 30 above. Now, at some point, we would assume the reaction rate would go fast, but if the temperature gets too hot, then the protein unfolds. So it'd be interesting to see that maybe the temperature, the rate will increase, and then maybe even start to come down again. That wouldn't be completely a surprise if that were to happen, because most proteins will fall apart at some temperature. Some stay together really stable at high temperatures, but a lot of them aren't. And so it'll be interesting to see how stable catalase is. I imagine it's fairly stable enzyme, since we're dealing with like dried yeast and this enzyme is still active. So I imagine it's fairly stable. And then finally, the effect of pH. This will be your last data table. So like I said, you don't need to do all 3 of these today. I'm going to do the first one with you, and then I'll stick around while you do the second one. The third one you may want to do a little bit later, because I said it's pretty involved, and you want to really concentrate on getting the dilutions just right, because it's fairly complicated. So, any questions before we begin?
I have a question. So
Yeah.
for the depth of the solution, how do we measure that? Would that be like with a ruler, or is that like on the cup, or how do we measure that?
Oh yeah, you use the ruler. So we got the little cup. You just measure how far it is from the bottom of the cup to the water line.
Okay, thank you.
Yeah. So you should have. There is a ruler included. Hopefully you still have it. I'd lost mine. Luckily, I found another one. So why don't we, since this one's kind of complicated, why don't we take like 15 minutes to get all our stuff together? It's a lot of stuff. So I'll pause and we'll come back at 3 and get going on the first one. Any other questions before we take a break? Okay. I will see you in a minute.
I have a question.
Oh, yes.
If I don't have bottled water or filtered water, do I need to boil water, or can I just use faucet?
Yeah, just use straight up water. You're in San Francisco, right?
Yeah.
Yeah. I've got this fancy new coffee maker. So I was looking at the different water hardness in the area. And we in Pacifica and in the peninsula, and in town, the water is pretty soft, meaning there's not a lot of metal cations in it. So I think you'll probably be okay. Where I'd be concerned with, like, there's certain parts of California, like just insanely hard water. And if you have a lot of, so you know what the difference between soft and hard water is, hopefully? No?
It's a lot of minerals in
Yeah, minerals,
water.
exactly. So if you have, why they're called hard is because it's difficult to form soap bubbles, which generally soaps are negatively charged. They have, they're fatty acids. So they have those long chains, which are hydrophobic, and then they have an acidic part. They have the carboxylic acid group, which is hydrophilic. And so they form a bubble with the hydrophobic on the inside, hydrophilic on the outside. But if you have a lot of divalent cations, like the +2 charge, like calcium +2, iron +2, if you have a lot of those metals around, they bind those carboxylic acids on the fatty acids, and they prevent them from forming bubbles. That's why your dishwasher and your clothes washer doesn't work very well in hard water, because it has a really hard time making bubbles. But it seems like the water around here is fairly soft, so I think you should be okay.
Okay. That's
Okay.
good to know.
All right.
Okay.
All right. So we'll see you in a minute. Yeah, so I just noticed there was something wrong with my thermometer. There's a bubble in it, so it's not working properly. I was wondering why it said it was 5 degrees in here. It is not that cold. So, hey, buddy. Luckily, I have a digital thermometer that I use for cooking. So if you have one of these, this is fantastic. You get really accurate temperatures and almost instantaneous. So my water is about at 36 degrees. So by the time I weigh out my yeast, it'll probably be perfect. So let me get all my stuff together. So I'm going to weigh out my yeast. I want grams. There we go. Tear that. So this is the yeast that comes with this particular kit. I think there was also some instant yeast before. I'm not sure what the difference is. They're probably the same. Okay. Yeah, so 2 grams is a lot more than I thought. There we go. And perfect. My temperature is now 34.9 degrees. So we're right on. So remember, you just fold that up. It makes it easy to, and then just tap it all in there. The best smelling thing in the world. So it gets all cloudy like this. You just keep stirring it. See how long it says to stir this for. It doesn't really say. Basically, you just keep stirring it until all the yeast is suspended. Obviously, the yeast aren't going to dissolve. So you want a fairly even suspension. Okay. So here's your medicine cup. And 20 mils. See, let me mark it with a pen here. "20 mils is about 3/4 of the way up or so. I'll just pour that in there. So this will be my 100% catalase. So pretty easy to see which one is the catalase. And then I've also just got some filtered water that I'm going to use. So next I'm going to make up my peroxide solution. Here's my 10 ml graduated cylinder. I'm just going to label this one my peroxide. So yeah, if you don't have a, I couldn't find the marker, the wax pen, so I'm just using a Sharpie. So 10 mils. And 10 mils of water. There's our 10 mils of water. Just give that a little shake to get that stirred up. So this is the distance we're going to be measuring here, from the bottom of the cup up to that 20 mil mark, or wherever it is. I'm just going to measure that. You're going to want to measure it in millimeters. And it looks to be, there's a 0 in this stupid thing. Here we go. Looks to be 20 millimeters, shockingly enough. There you go. That makes it easy. So 20 millimeters is the distance. So now I go to my plate. I'm going to make my 5 different dilutions. So one of my bulbs will be catalase and the other one will be water. So I'll label them so I don't mix them up. And water. Now notice on these plates, there's actually letters and numbers that helps you orient them. So there's A, B, C, D, and then, or actually, sorry, A, B, C, D, E, F, and then 1, 2, 3, 4. So you want A1 in the top left-hand corner. No, actually it goes the other way. Usually these have letters and then numbers. These have, it's A, B, C, D, and then 1, 2, 3, 4, 5, 6. I'm used to 96 well plates, so they're labeled a little differently. So remember, so the first one is just water. So take my water, and you want 20 drops. So 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 13, 18, 19, 20. So that gives you about that much, 20 drops. Each drop is probably around 1/4 of a milliliter. And the next one is 15 drops. 15. And then the next one I do 10. 1, 2, 8, 10. And then 5, and then none. Five. And for the catalase, I just do the opposite. So I start with none, and then 5, 10, 15, 20. Yeah, don't be afraid to mix it up a little bit. Just make sure you have a nice even suspension. One, 2, 3, 4, 5. 2, 3, 4, 6, 7, 8, 9, 10. 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. So you can see as you go across, it gets a lot more dense. So it's fairly easy to see which direction that's going. And you just shake, you sort of tap the plate to get it mixed. So now I want to make my discs, which probably would have been a good idea to do before doing all this stuff. So 1, 2, 3, 4. Oh, stupid me. I doubled this up, so I got 2 discs. Now I got way more than I need. Okay, that's fine. Yes, so if you do the 2-hole punch, they're all going to be about this big, pretty small. So you take them with the pair of forceps. You push it down to the bottom. You want to make sure it's completely soaked in. Getting it out might be a little tricky. There we go. And then just dab it on the side. So now you've got a nice wet disc. Take our peroxide. Oh, I need to get my timer before I drop this in there. That was stupid. Let me get my timer. Timer. All right, got my timer ready to go. Here's my disc, and I'm going to drop it, put it in the solution, the 1.5% solution, and push it to the bottom. There, it's now on the bottom. Start my timer. This may be a while. "30 seconds, it's still, oh, it's starting to move a little bit. Past a minute. I want to make sure I have it's not stuck to the bottom. Nope, it can move. Okay. Two minutes. Man, it's taking forever. This may be in millimeters per minute rather than millimeters per second. Makes me wonder why we had to dilute the peroxide. It's not like this reaction is super quick. Man, I'm gonna give this thing like 5 minutes and then I'm taking it out, trying it again. You basically see like one bubble and that is it.
What percent was that, Professor?
1.5% peroxide. So you dilute it 1 to 1, 10 mils of 3% peroxide and 10 mils of water. But I'm beginning to wonder why we needed to dilute it at all, since this is taking so long. Almost 4 minutes now and it has not moved. Oh man, this thing is just not moving. Maybe I bent it or something. I don't know if that would make a difference. All right, we're coming up on 5 minutes and nothing is happening. So I think I'm going to try that again. All right, I'll try that one more. All right. Here we go. Put it down on the bottom and start. Yeah, the first one I put in there, I think I may have pushed it a little too hard. It may have actually like stuck it to the bottom somehow. So this one I just sort of just let sink by itself. Well, if the point is that an uncatalyzed reaction really doesn't happen at all, they're making their point quite well, I would say. I mean, not only is it not floating to the top, it's not moving at all. I don't see any bubbles being made. Does anyone manage to get the 0% to float to the top at all?
Mine, none of my trials floated.
None of them?
Nope.
After how long? But how long did you leave them?
4 minutes.
Okay. Yeah, I think that's kind of the point. It looks like. Have you moved on to the 5%, Ryan?
I did the 25% diluted catalase, and those didn't yield any results whatsoever. But the 50% dilution of the catalase, it started to show up.
Wow, even the 25% didn't do anything. That's surprising. Yeah, I'm coming up on 4 minutes with Bupkis here. mean, so if your rate is 0, it's 0. That's yeah, I'll put that down as a 0. Okay. I'm going to try the 25, see if I get anything. You don't really see a lot of bubble formation with the 25. Well, but the 50, you're starting to see it, are you, Ryan? Oh, there it goes. And 35 seconds. Okay, finally got something to work here. Yeah, I got one of the 25% to pop up in 35 seconds, but maybe I didn't rinse it enough. So let's try that one again. Okay. All right, second trial, 25%. Yeah, this one's taking longer. So, oh, there it goes. $45. Yeah, I think there's going to be a lot of scatter in this data based on how well, how much enzyme you get off of the off of the circles. If you don't dab it a lot, you're going to have a lot more enzyme attached. Yeah, because 35 and 45, that's a pretty big spread. All right, one more. Oh, 33 seconds. Maybe let's do one more. Since these are taking a lot less time. Hmm. 33. Yeah, that's fairly clear. Okay. All right, let's move on to 50. It's making me think the 100% is going to be fairly instantaneous. $18. Yeah, much faster. What kind of times are folks getting? I'm getting around 18 seconds for the 50%. I guess everyone's probably going to be a little bit different based on the size of their one hole punch. If you have a larger punch, obviously you're going to make larger squares. It's going to take more gas to float them. Fifteen point three. That was 2. Four point six. Okay. $75. No. 75% only took 8 seconds that time. It was definitely getting faster. Yeah, I'm seeing a lot of variability, which isn't that surprising, I think. So I'm doing these 4 times and then throwing out the one that looks odd. Two. Okay. So is everyone seeing it speed up fairly dramatically? I'm going to do the 100% now. Should probably just pop up as soon as I put it in. Okay. So are people seeing a lot of spread in their data? There like big differences between individual trials? Is it just me? So Madison, how are yours going? You're seeing a lot of difference between each trial?
I'm just starting it right now, but
Okay. So too early to tell. Okay. I think I'm going to go ahead and actually try the temperature control. I'm just going to pause for a sec, get that ready. All right, so for the temperature, you make yourself a little ice bath and you take your 1.5% solution and just put it in the ice bath till it's 10 degrees below. So the room temperature in here is 16. So I'm just going to put it in here until it's 6. And then try my trials again. I think I may have to make this again. This may have spilled. There we go. Interesting. Actually, the temperature of the peroxide is higher than the room temperature. It's around 20. So I want to reduce this down to 10. So when you're measuring the temperature for these, when you're making your hot water bath and your ice bath, you don't want to have the thermometer touching the bottom, because obviously that's going to be a lot colder. So have it about midway. It'll give you a more accurate representation of the temperature. Because right now, if I look at the bottom of the cup, it's 13, well, 12 degrees, and then midway up, it's about 15. So big difference. And it's taking a lot longer for it to cool down than I thought. You fuzzy girl. Almost there. Okay. Now I got this down to about 10. Yeah, 10 degrees, pretty much taking about twice as long. So we'll see if that holds up. Jerome. Yeah, I found it makes a big difference. You need to have them sitting flat on the bottom. If they're not sitting flat on the bottom, they come up a lot faster. And I started the clock on one of them before it was completely flat on the bottom. Yeah, and it came up almost twice as quickly. I'm just going to ignore that one, do one more trial. Make sure it's flat on the bottom. Okay, that looks good. So I'm going to do one trial with slightly above temperature, and then I'm going to plot these out, see what they look like. Now trying 30. Okay. It's okay. Yeah, I'm not noticing a huge difference between 20 degrees and 30 degrees. Okay. We'll try one run at 40, see what it looks like. Really need hotter water. There we go. All right, let's try 40 degrees. Here are my forceps. So people have been seeing a big difference in the temperatures. 20 degrees above, I'm getting a definitely faster than room temperature and 10 degrees above. Get that bug germ. Okay. All right, so I've got some data collected. I'm going to take a break to clean this up a little bit and then come back and do a little plotting.
And at 25%,
Mm-hmm.
I got the filter paper was standing upright at 1 minute and 30 seconds, and it slowly started to float up top,
Okay,
like vertically.
right.
So is that like,
Yeah, as soon as it hits the surface, you stop the clock.
oh, okay,
Yep. Yeah.
okay.
Mm-hmm. Yeah, so I didn't realize that. Yeah, there's so many different sizes of one hole punches. So like, yeah, mine look pretty small. So I think mine are going to be faster than most people's. Because yeah, it sounded like a lot of you at 25%, they weren't moving at all. And I was getting times of, less than a minute. So I was going to go with the percentage first. %, 100%. So 35. 45. 43. 32.3. $18. 17.8. 16.3. 24.6. 0.1. 15.2. 12.2. 7. 0.1. All right, let's plot these out, see what they look like. Of course, that's time, and I actually want millimeters per second. So by C3. D3. Yeah, so since these are times in seconds, I'm converting them to millimeters per second by taking the 20 millimeters and then dividing them by the time. So, oh, no, E3. Oops. There we go. So, not what I'm looking for. Oh, I see. So I have to get these into a slightly different format. So damn it. 0.0. All right, that's what we want. Yeah, so you can see here that there is a very nice correlation between the concentration and the rate. So I've got 0 here, and then this, or no, 25, sorry, this is 25, 50, 75, and 100. And it looks like a nice linear relationship between them. So that looks pretty good. It's going to need a little more time to get to fit this, but I will work on that a little bit more. Okay, so does anybody have any questions about finishing this one? So you see what the kind of plots we're looking for. I will just put them up on a whiteboard here. So in general, oh God, they're not letting me do the whiteboard again. Let's try. Okay. We'll draw on this. So the first one, oh, no, not letting me draw. No, can't draw on this either. See if I can draw on this. No, can't draw on this either. Yeah. Hey. Yeah. Unfortunately, Zoom is not letting me draw on anything, which is a pain. So hey. So the first plot will be concentration of enzyme on the x-axis, and then rate on the y-axis. And it looks like that should be fairly linear. So then the next one will be temperature on the x-axis, and then rate on the y-axis. And then the final one will have pH on the x-axis, and then rate again on the y-axis. And I don't expect that's going to be linear. You're probably going to have some sort of curve with a maximum wherever the best pH is, which most likely will be around between 6 and 8, I'm assuming. So the first two are relatively straightforward. The third one is going to take a little longer, as I mentioned. Are you working on that one, Ryan, the third one?
Not yet, still finishing up the temperatures.
So how did the temperature one go for you?
Getting better results. I'm at 10 degrees above, and I'm seeing a slight increase in the rate as we're going up.
Yep. Yeah, unfortunately, I had to change my peroxide solution, and so I seem to get different results. But yeah, there is definitely a big difference between 10 degrees was slow, 30 degrees was faster, than 40 degrees was much faster. So what I'm going to do is I'm going to plot these and then post them for you guys to give you an idea of what it is we're looking for. So any other questions from folks before we need to take these dogs for a walk before they eat me?
For the activity 1,
Yeah.
is it common for it to be like inconsistent with like how long it takes for them to bubble up?
Yeah, I saw quite a bit of spread between, I did them all 4 times because I saw a little bit of spread in between. So what I did was like do it 4 times. If one of them looks like it's different from the other 3, then I just tossed that one.
Okay.
So are you seeing like a huge difference?
Yeah, the largest difference was the first trial was it took 40 seconds for it to rise at the top, and then the second one it took about 2 minutes and 10 seconds.
Oh, wow. Yeah, that's a huge
Yeah.
difference. Yeah, I wish there was some way, like when you take it out of the yeast solution, we could, it just says, you know, to rub it against the side of the
Well,
wells, but that's not a very consistent way of getting like this very same amount of yeast extract in every one. So I think that's going to lead to some variability.
is it
Yeah.
could it be like how long you like submerge the circles?
That could be 2. I mean, I left it, well, I just sort of just left it in till, you know, for maybe like about 5 seconds or so, and then
Okay.
took it out. I mean, if you left it in for like a minute, I don't know, it probably would soak up a lot more extract. So yeah, make sure you put them in for approximately the same amount of time each
Okay.
time. That'll help with the variability too. Yeah, that's a good point.
Okay. Thank you.
No worries. So did you have a 1-hole punch, or are you cutting these out?
I have a punch.
Oh, you do? Okay.
Yeah.
So approximately how big are the circles?
Um,
I'm going to measure mine because I forgot to measure them. Yeah, so mine, you can see mine are pretty small. Oop. There we go. So yeah, they're like they're like 5 millimeters across. So yours probably, are yours bigger than that? Yeah, like 5 millimeter diameter.
half a centimeter.
Yeah. Yours are the same size?
Yeah.
Oh, okay. All right, any other questions? How you doing, Jessica? How's it going?
It's going well. I just started the temperature one because I had to cut all the squares.
Oh, you had to cut them out.
Yeah,
drag.
that took forever.
Yeah, I can imagine. So how did you manage to keep them like a uniform size?
So I measured first and then I just cut it. Yeah.
There you go.
So I measured them on the filter like this.
So how big are yours?
6 by 6 millimeters.
6 millimeter. Okay. So yours should take a little bit longer then. And Dee Dee, you feeling okay? All right, cool. All right, everyone. So yeah, if you have any other questions, just drop me an email. Also, we'll be having office hours tomorrow at noon. So And remember, Thursday, you've got off. Yay. And I did remember to change the assignment to next week. I actually remembered something. So yay for me. Anyway, good luck, everybody.
Thank you.
Have fun.
Thank